page 250 in your textbooks, you had questions 8 through 11, 14, 15, and 17. And also at page 251, problems 1 through 9, the odd. So we're going to take a look at those questions and those problems. All right, good. Question number 8. Distinguish between transverse and longitudinal waves. Audrey, what did you have?
Transverse waves are particles that move perpendicular to wave direction, while longitudinal waves are particles that oscillate parallel to wave direction.
I wouldn't say they are particles that oscillate, but they have particles that oscillate. Or in a longitudinal wave, the particles oscillate, something like that. But yes, you got the idea. Good. Number 9. What pulses alternate in a longitudinal wave? We said for a transverse wave, it's crest and trough. But what do you have in a longitudinal wave, Kendall?
A compression pulse alternates in a longitudinal wave.
That's one of the two pulses. Did you get the other one? Audrey?
Rarefaction pulse.
Good. Compression and rarefaction pulses alternate in a longitudinal wave. Should have been our answer for number 9. Compression and rarefaction pulses. Number 10. What's the most familiar kind of longitudinal wave? Back to Kendall for redemption.
The most familiar kind of longitudinal wave is sound.
Good. Sound waves are the most common longitudinal waves. Number 11. What is the law of reflection, Audrey?
The law of reflection is when the angle of incidence equals the angle of radius.
I don't think you mean angle of radius. And we wouldn't say the law of reflection is when. We'd say the law of reflection states that the angle of incidence equals the angle of anyone? Reflection. Angle of incidence equals the angle of reflection. There we go. So the law of reflection states that the angle of incidence equals the angle of reflection. Skipping to number 14, when waves enter a medium of slower wave speed, how are they refracted? Let's go back to Audrey for redemption.
When waves enter a medium of slower wave speed, they are refracted because the waves bend toward the medium.
Okay, they're refracted, not toward the medium, but what does the refraction go? We talked about it yesterday. Waves are refracted either toward or away from the normal. There we go. So when waves enter a medium of slower wave speed, they're refracted toward the normal. Number 15, when is diffraction most pronounced? Back to Audrey.
Diffraction is most pronounced if the gap is about 1 wavelength in width.
Good. If there's a gap the waves are passing through, again, 2 or 3-dimensional waves passing through, if its width is about a wavelength wide, then you'll get really pronounced diffraction. And number 17, distinguish between constructive and destructive interference. Kendall.
Constructive interference is when the
It's not when anything. Occurs when. You say destructive, constructive interference occurs when. How about that?
Occurs when the present displacement of a particle in a wave medium is greater as a result of superposition. And deconstructive interference.
Not deconstructive, but destructive.
Destructive interference is exactly the opposite with a smaller displacement as a result of superposition.
There we go. Very good. All right, let's go and review some things, and then we'll get to our problems that we worked yesterday. We're talking about waves. Michael, what is a wave?
Transfer of energy.
Good. A transfer of energy through, specifically a medium that is elastic. There we go. A transfer of energy through an elastic medium. Good. And we said there's really 2 broad categories of waves. One in which the waves, as the wave moves forward, the particles will oscillate up and down. The other way that occurs or has particles in which they'll oscillate back and forth along the same line as the energy flow. What are those 2 major groups of waves, Audrey?
Transverse and longitudinal.
All right, since she had the homework question, Michael, which one's which?
Transverse is up and down. Longitudinal. Okay. Transverse is like this, and longitudinal is like this.
Okay, so if it were on a quiz or test and you had to write it, the 2 key words to remember is parallel and perpendicular. Because you can't even say, well, in a transverse wave, particles move up and down. Well, right now, particles are moving up and down, and that's a longitudinal wave. Right? Perpendicular. If the particles move perpendicular to the wave, that's
Transverse.
And if they move parallel or in the same line with the wave, it's longitudinal. There we go. We also said that we can classify waves based on the way in which they travel. For instance, if a wave travels in a singular direction, class, we would describe the wave as being a singular direction, often along a wire or a connector. One-dimensional, right? We said it's a good thing sound isn't a one-dimensional wave, because otherwise I'd literally have to have my mouth aimed right at your ear for you to hear anything. Now, I know it feels that way with elderly people. Sometimes you have to get right up in their ear, but sound travels obviously in all directions, so it's not a one-dimensional wave. We said that a wave that, for instance, most water waves, that they can travel outward along a plane are referred to as two-dimensional waves. And it's important to remember that because the wave is traveling outward in all directions along a plane, what happens to the strength or the energy of that wave class? It dissipates. It begins to weaken as it spreads outward. Concentrated energy, but because it's spreading outward, taking a bigger area, if you will, that wave weakens. And then finally, a wave that travels outward in all directions, three-dimensional wave, and we need to remember then because it's traveling not just outward this way, but outward all ways, a three-dimensional wave is going to dissipate the quickest. It's going to weaken very rapidly. We said sound, of course, is a good example of a three-dimensional and longitudinal wave. Going back to the transverse wave, we said there are two pulses in a transverse wave. Kendall, they are?
Compression.
On in a transverse wave. That's the perpendicular one. The wave will go up to a high point called the, and the low point called the. So the two alternating pulses are basically a crest and a trough, right? The up pulse and down pulse, or the crest and the trough. And we said that a single disturbance, I already used the term class, but a single disturbance is called a wave pulse, right? We even looked at that with a longitudinal wave yesterday, right? I allowed a compression pulse to travel or a rarefaction pulse to travel along. And I just said them, but what are those two longitudinal wave pulses? That's transverse. Longitudinal wave pulses. Compression and rarefaction pulses, good. We talked about the distance between consecutive points or corresponding points on consecutive waves in a what's called a wave train. For instance, if I kept releasing bits of the slinky, right, I could get more and more compressions to go along. Or perhaps if I oscillated the end back and forth, I could get the compressions and rarefactions to move along. If I measured from one compression to the next compression, or from one point of rarefaction to the next point of rarefaction on the next wave pulse, that would be giving us class the wavelength. It could also be in a transverse wave, crest to crest, trough to trough. Distance between corresponding points on consecutive waves is called class wavelength, represented by the Greek letter lambda, and it's measured, since it's a wavelength, class, it's going to be measured in either meters or feet. We said that if I'm looking at compressions and rarefactions, maybe going past, I noticed that, wow, in just 1 second, 5 compressions and rarefactions just went past. Well, the number of waves that travel by a point per second is called class frequency, represented by F, and frequency is measured in hertz. If I were to find the product of the wave's lengths and the wave's frequency, wavelength times frequency, class, gives me wave speed, or we could say velocity. This is one of our equations for wave speed we used in our homework. There was another one, though, that we used related to a wire or a string or a cord of some kind, a rope, any kind of connector. I said we can find the speed that a wave can travel through based on two things. Audrey, what are those two things that affect wave speed through a wire? Or think of a piano string.
Force.
Well, you're not wrong, but specifically a force of tension. There we go. How tight you tighten the piano wire. Or piano string, I guess.
I know the other one's mu.
It is mu. If you look in the back of the baby grand and you look at all the wires, what do you notice about them?
Different length.
They are slightly different lengths, that's true. What might be even more obvious is you look at the high end versus the low end. You're not wrong on the length, by the way. That's not a wrong thing. That's just not helping us with mu. Michael? the thickness, right? You have really fat wires on this end and skinny strings up on that end, right? So the mu is the thickness, or the mass per unit length is what it's called. What's that equation, Audrey, for wave speed traveling through a wire or a string?
The square root of F sub T over mu.
There we go. And so there were the two equations. Well, there was one more. Remember I said a moment ago, if we watched a bunch of oscillating particles, we noticed 5 sets of compressions and rarefactions. 5 full waves went by a particular point in 1 second. Well, that means it would take like, what, a fifth of a second for a single wave? What do we call that time for a single wave to pass a point, class? Period. Period. And a period we represent with the letter capital T, right? It's capital T because it's time, if you will, measured in seconds, right? How are period and frequency related, class?
Reciprocals.
They are reciprocals, right? So period is the reciprocal of frequency, or vice versa. Frequency the reciprocal of period, and we may need those equations in this chapter as well. Those are really the only 3 equations that we had in this chapter. I think the only thing I can think of now that I didn't already review, in a transverse wave rather, the resting position, the balanced position, class, we call equilibrium. The displacement from equilibrium to either the crest or trough is called amplitude. Now, the same can be said of a longitudinal wave, right? As we spread the slinky out, I'll go and do it because it's fun to play with slinkies. As we spread the slinky out, we notice how the particles are arranged, right? We see what their spacing is. Well, as we release a bunchness, we notice that the particles went in certain places from being, like this, but in certain places they bunched up a little bit tighter. The displacement from equilibrium there is still called, class, amplitude. It's just the distance of the natural state, the equilibrium state, to the compressed state, or the rarefaction state would be the expanded state. You can still have amplitude on those. It's not as maybe visible as we would be with the transverse wave, but amplitude still applies. Let's take a look at these math problems, and we'll go over some of the other stuff we looked at specifically yesterday in section 16.2. And problem number 1, read it for us if you would, Audrey.
Sound waves have a frequency of 1,000 hertz. What is their period?
Now again, this isn't all sound waves, okay? Some specific sound waves have this frequency. For these specific sound waves, what would be their period, Audrey?
0.001 hertz.
Well, period's not measured in hertz. Frequency is. Period is measured in
Seconds.
And the only bummer is, how many sig figs are we supposed to have? I wish they hadn't done this.
4.
Yeah, they should have just said 1,000 hertz and left it at that. But they did 1,000 point. So technically, our answer should be, Audrey.
0.0010.
That would still be 2 sig figs. 0.001000 seconds, which is really annoying. It would have been great if they just left it as 1 sig fig, but they didn't. So 0.001000 to get our 4 sig fig seconds. Number 3. It says, what is the wave speed along a string under a tension of 105 newtons if the mass per unit length of the string is 5-3 kilograms per meter? And what that means basically is if you have a 1 meter long string, it'll weigh 5 grams. It'll have a mass of 5 grams. So it's a pretty thin string. Pulled to a tension of 105 newtons. How fast will a wave go along that? Kendall?
0.525 meters per second.
Audrey?
I had 0.53 newtons.
Okay, well, it wouldn't be newtons, it's wave speed, so we're looking for meters per second. We're looking for this equation here this time, right? So we know the tension is 105, and we're going to divide it by 5e-3. And then we're going to take the square root of all of that. So 105 divided by 5e-3, and then take the square root. And what do we get now?
144.913.
Yeah, 144.91, blah, blah, blah. Rounded to, looks like 2 sig figs.
140
And we said speed, or velocity, but speed is measured in meters per second. There we go. What did we do on number 3? Because you both had very similar answers.
I think I multiplied.
Okay.
I did too.
All right, does it make sense now?
Yeah.
All right, let's take a look at number 5 and read that one for us, Audrey.
A string has a tension of 5 newtons with a traveling wave propagating along it at 6 meters per second. What is mu?
Ooh, propagating, that is such a great word. All right, so we know the wave speed this time, right? We know the 6 meters per second. We know the tension is 5 newtons. The question is, what is mu? Ooh, what do I need to do to get mu by itself? Michael, I know you didn't do this one because you had the homework passed, but what would I do to get mu by itself?
Square velocity.
So really square both sides, but it has the net result of squaring velocity and knocking out the square root here.
And alternate.
Alternate, that's that second key. So mu equals,
S of t over t squared.
there we go. Did we get this equation? Did we rearrange it this way? All right, Kendall's yes, Audrey's no. Audrey, questions?
I did it backwards.
Oh, okay. All right. And so, Kendall, then, you plugged in the 5 Newton tension, you plugged in the 6 meters per second, that squared it, and you got what value for mu?
I forgot to square.
Ooh, okay. Anyone? 0.138, or rounded to 0.14. And what do we measure the mu in? That mass per unit length.
Kilograms per meter.
Good mass, kilograms per unit length, meters, kilograms per meter. So 0.14 kilograms per meter should have been our answer on 5. Questions on 5. Number 7, read it for us, Kendall.
What is the wavelength of waves with the frequency of 2 hertz and a speed of 13.6 meters per second?
All right, what equation do we need to use here, Kendall?
V equals lambda f.
But it tells us to find the,
Find the wavelength.
so lambda is going to equal what?
V over f.
V over s. So we should have taken the wave's speed divided by the 2 hertz frequency to get what for the wavelength, Kendall?
6.80.
6.80, because we need the third sig fig, meters. 6.80 meters. Do we have that, Audrey? All right, good on 7. And number 9, read it for us, Audrey.
What is the frequency of waves with a wavelength of 0.35 meters and a wave speed of 5.2 meters per second?
All right, what equation do we need for this one, Audrey?
So the lambda equals v over f.
Right, except we're not solving for wavelength, we're solving for,
Frequency.
so either solve either one of these for frequency. It really doesn't matter, we just same thing either way.
I got 15.
I'm not looking for the answer, I'm looking for what's the equation.
V over lambda.
There we go, V over lambda. So you plug in the wave speed, you'll divide it by the wavelength, and now, what did you get for your answer?
15 hertz.
I got 15 hertz also for the answer. I'm not sure if that was rounded or not, but I wrote 15 hertz in my book. All right, did we also get 15 hertz? All right, questions on the math. Again, just 3 equations. Reciprocals for frequency and period, V equals lambda f, V equals the square root of f sub t over mu. So not a lot of equations to memorize, which is a change from normal for us, right? A little bit of a, this is nice, you know, so enjoy it, but questions at all on that? All right, yesterday we talked about different wave behaviors. And so before we get into our new notes, let's talk about what we looked at yesterday. 3 wave behaviors. One of them, we talked about a wave as it goes through a medium. If it enters a new medium and it has to change speeds, what will happen to a wave anytime it changes speed? Class?
It bends.
It bends. What's the technical word for bending? That's a great way to think of it. What's the technical term we need to know?
Diffraction.
Not reflection. Refraction, there we go. So refraction is the bending of the wave as it does what again, class? Changes speed. Now, again, I say anytime it changes speed, it'll refract. That's not entirely true. If the wave is heading straight on, straight in line with the new medium, it won't refract at all. Because refraction, and reflection for that measure, are measured with respect to what line? The normal or the perpendicular. So if this is the interface between 2 media, if the wave is coming along the normal, there will be no refraction. But if it's coming in at an angle of incidence, we call it, theta sub I. If it's coming in an angle to the normal, if it speeds up, class, instead of continuing its present course, it refracts. It speeds up. Think about your garage. You don't speed up toward the garage. That's a big crash waiting to happen. Speed up, it's going to go away from the normal. Make this angle greater than the angle of incidence. If, however, it slows down in the new medium class, it refracts toward the normal so that the angle of refraction is smaller than the angle of incidence. Make sense? Okay, so again, the bending of a wave class is what makes waves refract? Changing speeds. If it speeds up, away from the normal, and if it speeds up, away from the normal. But if it goes faster, away from the normal. If it slows down, toward the normal. Okay, questions on that? All right. If a wave strikes a surface, it will turn back into the first medium. What do we call that turning back of a wave after it strikes a surface? Reflection. Right? If it strikes a surface and it bounces off in a sense, that's reflection. And again, if the wave comes in head on to a boundary, it'll reflect off head on as well. No big deal. However, if the wave comes in at an angle to the boundary, it will reflect off, not straight back along its own path, but rather, we said the law of reflection class says that the angle of incidence equals the angle of reflection. Very good. And both of these angles, class, are again measured with respect to the normal. So at the point of contact, if we imagine a perpendicular at that point, this incident angle will equal this reflected angle. So the turning back is reflection and the angles stay consistent, again measured with respect to the normal. The last wave behavior we keep trying to say is diffraction. What is diffraction, class? It's spreading out. So the wave, for instance, may be blockaded by other things, but as long as there's a narrow opening, the wave can pass through, spread back outward, and regroup or recover itself. As it goes through, if a wave encounters an obstacle, it'll regroup around the obstacle and keep on going. And again, what kind of waves can do this? Yeah, that's an example, but in general, 2- and 3-dimensional waves. A single-dimensional wave, right, it just travels along a straight line. It hits a boundary, it's going straight back. It's going to reflect off. If it comes to an opening, it goes straight through, right? No problem. It's when it's a 2 or a 3-dimensional wave that's capable of spreading outward for diffraction. Okay, so bending, refraction, spreading out, diffraction, and changing direction. Actually, that was a bad one because it could be either one. I was thinking changing direction as it goes through would be refraction. Striking and bouncing off would be reflection. Okay? Clear as mud? It bends. Refraction. It bounces off. Reflection. It spreads out. Diffraction. Okay, keep the 3 terms. They're all very similar in the way they're, they all end in shun for one thing. They all have a ra or something in the reflect, refract, diffract. They all kind of sound similar, so keep them straight in your heads. All right, next thing in your notes. You read about this last night in your homework reading, superposition. Superposition. Superposition is the result or addition of multiple waves, the result or addition, not addition like the late edition, first edition, second edition, like addition, result or addition of multiple waves acting simultaneously in the same medium. Superposition is the result or the addition of multiple waves acting simultaneously in the same medium. The result or addition of multiple waves acting simultaneously in the same medium. For instance, you're in the pool or the hot tub and you've got friends or family with you. If you were alone in the pool and you were splashing, waves would emanate outward from you. But if there are more than one person in the pool, both of you making waves, right? The whole pool just seems very strange with the wave pattern. There's not really a pattern to it, it seems. And the reason is you're making waves, they're making waves, and the waves, as they collide, they basically add on to each other, and so it produces what could be a very strange wave pattern. The book shows an example of a rope, and it shows that if you used a single small spring, it would produce a certain oscillation. If you used another larger spring, it would produce a more rapid oscillation. We're down on page 248. But if you could actually combine the two together, and by the way, the whole thing with the pulley, that's just keeping some tension in the rope so it stays nice and tight. When you add the two things together, it produces a very strange, non-sinusoidal, Audrey and Michael, you know what I mean by that, a non-sinusoidal wave. It doesn't have a nice normal pattern to it, is basically what that means. It's just weird, and it's formed because of the two waves essentially being added. We looked at different sine and cosine curves, you'll remember, Audrey and Michael, in pre-calculus. And we didn't do a lot of this. I think I showed one of these right at the very end of that graphing chapter, where if we were to take a typical sine curve, for instance, and then we were to take, for instance, maybe a sine curve that has been inverted, maybe the amplitude has been squished, and so maybe we had a inverted sine curve, something like that. Well, if you were to add the two together, 0 plus 0 equals 0, 1 plus a half equals a half, 0 plus 0 is 0. These all are fine, but then you're going to take this point that's here and this point that's here, it's going to equal that, and it's going to make a kind of a weird wave pattern if you were to actually add the waves. Well, superposition really is adding multiple waves together at the same time, and it gives you a really strange result. Look what they have there for their interposed, if you will, wave trains. They show a curve in black, and again, if you look at just the black curve, it's nice and rhythmic and good. If you look at just the blue curve, again, it looks kind of like a cosine curve, but it's still nice and smooth. But then when you add those together, you get the result of that red curve. Again, that's kind of what's going on, if you will, with the water waves. That when more than one person's in the pool, it's just making all kinds of different waves. You could even make the same phenomenon happen by yourself, because what's going to happen as the waves hit the edge of the pool? They're going to reflect back, right? They're going to strike that boundary and they're going to reflect back. And then the reflected waves will interfere with the waves that you're creating, and we'll get this really weird, just disturbed surface of the water, right? The pool looks very disturbed, even though you single-handedly are making the waves yourself. This is because you are adding waves together. The addition of waves, if it's specifically from opposite directions, which in a rope, they would have to come from opposite directions, essentially. If one person on either end, I suppose. In the water, you could have like all different angles of waves. But if waves collide from exactly opposite directions, we produce what's called interference. It's a form of superposition. Interference. It's a form of superposition. Interference occurs when two waves collide from opposite directions. Interference occurs when two waves collide from opposite directions. So superposition in general is in the same medium we got more than one wave happening at once. And so it looks weird. Or maybe even sounds weird, right? Sounds can superimpose on each other as well, can't they? Right? Crowd noise at a game. Why does it sound that way? Why? Your ear basically just says there is noise. Your ear doesn't even try. Now, if you listen very carefully, you can try to pick up individual sound waves, right? Eavesdrop on conversations, that can be great fun. But it just kind of sounds like noise because your ear is telling you there's so many different waves, sound waves going on right now. They're all just kind of superimposed on each other. It just sounds like a muddled mess. Now, different frequencies can rise above, like the referee whistle. Everybody hears that despite the other crowd noise. Right? There's certain noises that your ear can distinguish from others. But that's superposition. Waves from opposite directions, though, produce what's called interference. Three types of interference. First of all, we have what's called constructive interference. Constructive. How many of you, when you were younger, you remember your parents telling you, find something constructive to do? Did your parents ever use that phrase with you? Find something constructive to do, boy. All right, or in Audrey's case, girl. Your parents never had to tell you that? Make yourself useful, kid? Did they ever say that? Go make yourself useful? Do something to help?
They never say constructive.
They never used that word.
I would have heard destructive.
Well, see, I use that term with my children specifically. Okay, you're being destructive right now. Find something constructive to do. Do something profitable, something that's going to help the situation. And one of the early things you do when you play with blocks, right? You build a tower, knock it down, build a tower, knock it down. Well, the trick is, I build the tower, Andy knocks it down. I build the tower, Andy knocks it down. Then it's okay. Now let me teach Andy to be constructive. Teach him to build his own tower. See if he can build it as tall as he is. Whoa, super cool, right? And so teaching him to be constructive. Constructive is the idea of building up, right? Destructive is Andy knocking the tower down, but constructive is building up. Well, imagine two waves are coming at each other from opposite pulses. If they were to sync just right, that as they collided, they both crested at the same time, you're getting the high energy level from both of them. What that will do will actually amplify. Superposition, you've got a high point plus another high point. It's kind of like what you see on that graph on page 248, right at the first mark, the first dot with the red. You see you have two relatively high points, they produce yet another high point. And so if two waves, as they collide, are both reaching higher energy level at that same time, they'll result in a larger wave pulse as a result. So, constructive interference. You need to know it generates a larger wave pulse. Constructive interference generates a larger wave pulse. Now again, this isn't exactly accurate here, but if two people are singing together and they're staying exactly together, they're generating the same sound at the same time, and so as their sound waves collide, it creates a larger wave pulse. Now that's not necessarily coming from opposite directions per se, but in theory, they're creating a larger wave pulse. It comes out sounding louder because two of them are singing. If they're off with each other, it just sounds garbled again. But constructive interference. And you see the picture there, if you will, of two waves that are about to both crest at the same time. It results in that larger wave pulse. That's constructive interference. The opposite is what Michael was famous for as a kid, destructive. Not necessarily destructive interference, but destruction. Destructive interference. This is where when the waves collide, maybe one is about to crest, the other is somewhere in the troughing, or the energy levels are different, and because they're on opposite ends, so to speak, the one weakens the other. And so a smaller wave pulse is generated. Destructive interference generates a smaller wave pulse. Destructive interference generates a smaller wave pulse. The example shown in your textbook is if you had a high amplitude wave cresting as a low amplitude wave troughs, as they collide, superposition says you add them, well, the result is a slight wind for the crest because it was greater. So we end up with a smaller wave pulse, and of course the waves continue moving on, or those pulses end up moving on, but we get a smaller wave pulse. That's destructive interference. The next one is complete destructive interference. Complete destructive interference. This would be the same situation as before, but if the crest and trough were of equal amplitude, their sum, when you add them by superposition, would be zero. They would literally, at that brief moment, cancel each other out. And you would get no energy at that spot. You get a dead spot, if you will. Complete destructive interference cancels out. It occurs when the two wave pulses cancel each other out. Know that phrase, cancel each other out. When the two wave pulses cancel each other out, that's complete destructive interference. Now, this is interesting from a sound perspective. I know you two, you've been to Pensacola, both of you, correct? Have you ever been down to Pensacola Christian College?
The location, but not the college.
Okay, but you've been to Pensacola, Florida, just not to the college. So you've been in the Crown Center, the great big building. Okay, when they built the Crown Center, it's a really big building, really pretty, all of that. And you know they have that balcony, right, that has that, it's that angled surface that faces out toward the stage. They discovered when they built it, I know this because my dad's into sound and audio there at the college, he was helping oversee the installation and the management of all the electronics that they use. They discovered that with certain notes that would be played by the organ, as they came out the speaker, they would reflect off that surface against themselves. And they would happen to cancel each other out at certain points in the audience, where you'd have dead spots in the audience. So what they did was they put panels, sound panels along the front of it. When they first built it, they weren't there. I remember going in right after it was built, they added those sound panels to absorb the sound to prevent the reflection onto itself to produce this complete destructive interference. If you would be able to generate a wave then that strikes and rebounds onto itself, if you could get a wave as it's traveling toward, for instance, some boundary, we actually did this in my physics lab in college, I told you about a harmonic oscillator, it's just a little piston that goes up and down really fast. Well, we attached the piston to the string, we had it going up and down really fast. Obviously what it does is it generates a wave that travels up and down. Now, if the wave perfectly hits back at equilibrium, maybe draw it more realistically here, what probably happens is it's not back to equilibrium yet. Then when it reflects, it kind of reflects up funny and everything's just weird. So the string just kind of is wobbling, and that's all you see is a wobbly string. But if you could time it just right, and what we do is we adjust the frequency on this thing to get the wave to just perfectly hit back to equilibrium. Its reflection is going to go back up this way. And the half wavelength point means you're going to hit equilibrium from both directions. Complete zero energy at that point. And then we can come back here at complete zero energy at equilibrium again. You could actually get the wave to form these little pockets. It was really cool to see. You'd actually see little, it looked like the string formed little pockets, but it was the same string. It was just vibrating really fast. And if you put your pencil on the string at any one of these points, you'd mess up the whole thing, but you'd also feel energy flowing through the pencil. But if you put it at these points, if you put it right at the points, you'd feel absolutely nothing. And the wave would pass completely undisturbed because you weren't blocking any of the energy flow. There was no energy at that point. If you can get a wave to reflect back onto itself like this, this is what's called a standing wave train. A standing wave train. And it uses this principle of complete destructive interference where the two waves are coming back at each other at just the perfect time. These points of no energy are called nodes. These points of no energy are called nodes. And again, it almost gives the illusion of like a jump rope, right? You see the person jumping rope, and you see the rope going round and round and round, but that's not what was going on. All it was simply going up and down, but it gave that illusion. These little pockets are called envelopes. You don't have to know that term, but you do need to know the term nodes. If you're watching on YouTube, I have a video in the description of this video, a link to a video rather. If you would, I want you to go and watch that video next. Here in just a moment. You'll actually get to see this demonstrated by a physics professor. We're going to do the thing, that demonstration here in this class, but we're going to go ahead and end the video here. Your homework for this evening, and we'll get that done before we play around with these standing waves, your homework for this evening is to complete a handout. And again, if you're watching on YouTube, that handout is, as always, in the description of the video. Short handout, only a couple of problems here for you. Making sure we've got the math down. Also study chapter 16. So we have wrapped up chapter 16, and you know what that means. Okay, so complete the handout and study over chapter 16 as we head into the weekend. Also, though, I need you to read ahead where we're going to be going on Monday. Read over pages 252 to 254. Read over pages 252 to 254. Now that we've gotten into waves, we're going to break down and look at specific waves. And we're going to focus on sound waves in our next chapter. Answer on page 264, questions 1, 3, and 4. Answer on page 164, questions 1, 3, and 4. One more time, the homework is to complete the handout and study chapter 16. In addition, read pages 252 to 254, and on page 264, answer questions 1, 3, and 4. So this time, if you're watching on YouTube, this video will end. Go ahead and watch the video link that's in the description.